This is a demonstration video on calculating equilibrium concentrations. So generally speaking, if I want to calculate equilibrium concentrations, multiple equilibrium concentrations, I'm going to use an ICE table. So let's look at an example of a reaction. So let's say that I have two dihydrogen sulfides going to make two hydrogen gas plus one S2 gas. And I have a Kc that is equal to 1.67 times 10 to the negative 7. Remember that K has no units. Because it's Kc, it's going to be in reference to molarity. And this is at 800 degrees Celsius. So K is temperature dependent. I might not need to use that temperature, but K at a different temperature would be a different value. So for this particular reaction, we are given the information that we have a 0.5 liter flask and that we have an initial amount of H2S that is equal to 1.25 times 10 to the negative 4 moles. So that's not molarity, that's just my moles. So to get my initial concentration, I'm going to need to divide by my liters here. And so we'll also say that we have originally no H2 or S2 in the flask. So to get my concentration of H2S, my initial concentration, so I'll put an I there, that's going to be 1.25 times 10 to the negative 4 moles over 0.5 liters. It's the volume of my flask, and so that gives me a concentration of 2.5 times 10 to the negative 4 molarity. So now I'm going to set up my ICE table. So I'll write my balanced chemical equation. So I've got 2 H2S goes to 2 H2 plus 1 S2. And I've got initial, change, and equilibrium concentrations. So I just determined my molarity on the previous slide. So my molarity initially is 2.5 times 10 to the negative 4 for my H2S, and I said I didn't have any of the products initially. So I've just filled a flask with H2S. I'm going to give it time to react. H2S is my only reactant. Since my reactant is being consumed, I'm going to put a negative in front. And because there are two of them, I'm going to say minus 2x. I don't know the amount that is going away. I'm going to be able to solve for that. H2 and S2 are my products. Because I have two H2s, I'm going to put plus 2x. And because I have only one S2, I'm just going to put plus x. So my reactants are negative. Okay, they're going away because I've got, they're being consumed. And my products are positives because they are being formed. So then my equilibrium concentration is going to be the initial amount with the change. So for my H2S, it's going to be 2.5 times 10 to the negative 4 minus 2x. I had 0 of the other two, so my equilibrium amount of H2 is going to be 2x, and of S2 is going to be just x. So now I can plug these values into my equilibrium equation. So just so we all are on the same page, my equilibrium equation is going to be the products over the reactants to their stoichiometric coefficients. So I have 2 H2s times 1 S2, those are my products, over the concentration of H2S, which is my only reactant, and I have two of those, so that will be to the second power. So if I plug in the values that I just came up with, that is going to be 2x squared times x over 2.5 times 10 to the negative 4 minus 2x, and all of that is going to be squared. So you can either do this algebraically or you can plug and chug. So what I need to do is put in my actual k value, which is 1.67 times 10 to the negative 7. So that's either going to have to be given to you, you're going to have enough information to find it. So we have just one variable, and that's this x in here. So if I plug that into my calculator using either the solve function or algebraically solving it, I get that x is equal to 1.09 times 10 to the negative 4 molar. So that happens to be the concentration of S2, but it is not the concentration of my other reactant and product, and I'm going to have to solve for those. So as I said, x is equal to 1.09 times 10 to the negative 4 molar, and that is also equal to the concentration of S2, because that is just equal to x. The concentration of H2 was equal to 2x, so I can plug in my x, multiply by 2, and that gives me 2.19 times 10 to the negative 4 molar. And then the concentration of my H2S is equal to my initial amount, which was 2.5 times 10 to the negative 4 molar minus 2x, and 2x is this amount. So if I plug that in, I get 3.13 times 10 to the negative 5 molar former concentration of H2S. So I solve for x, and then what I need to do is check and see if x is any of my actual concentrations, or if I have to do some further manipulations there. So x is equal to the concentration of S2, but H2 is equal to 2x, so I need to take that x value and multiply it by 2. And then H2S is equal to the initial amount minus 2x, and so I need to plug in that x value there and solve for that concentration. So the concentrations of my two products and my reactants are all different at equilibrium because of their stoichiometric coefficients and because of how much we began with. So some general strategy for solving for these type of problems. If I only have one unknown, then generally that's just going to be a plug and chug type situation, and I can use my equilibrium expression. So K is equal to the products to their stoichiometric coefficients over the reactants to their stoichiometric coefficients. So I could solve for a product concentration, a reactant concentration in equilibrium, or a K value. I just have to have only one unknown. If you are being asked, is the reaction at equilibrium, then you're going to be solving for Q, and you're going to compare that to a K. So is our reaction at equilibrium? We solve for Q, and then we compare that to our K value. So we talked about that in our notes. Q can be less than K, greater than K, or equal to K. If it's equal to K, it's at equilibrium. If it's not, then the reaction is not at equilibrium. And then if you're solving for multiple equilibrium concentrations, that's often an ICE table. So you would usually be given initial amounts in this case, and you'd have to determine what the equilibrium concentration. So most of the time here you're going to have a K value, and you're going to have initial concentrations, and then you will be able to solve for the equilibrium concentrations.